PID in PID control stands for proportional integral derivatives. To understand PID, we have to understand the mechanics of integrals and derivatives. I think you'll find this primer helpful as a tool for explaining PID to others in your team. In these days of computer-aided design and analysis tools, the need to solve a differential equation has been all but eliminated. This means that most engineers have lost touch with the concept of calculus and how it applies to the real world. This is a shame, and particularly in process control. The ability to visualize a problem mathematically is what really separates the real pros from the rest of the crowd. This will give you a real edge to understand what's going on in your controller. Here's a classic block diagram of a process under PID control. What's going on in this diagram? The set point is the value that we want the process to be. For example, the temperature control system in our house may have a set point of 22 degrees Celsius. This means that we want the heating and cooling process in our house to achieve a steady temperature of as close to 22 degrees Celsius as possible. The PID controller looks at the set point and compares it with the actual value of the process variable. Back in our house, the box of electronics that is the PID controller in our heating and cooling system looks at the value of the temperature sensor in the room and sees how close it is to 22 degrees Celsius. If the set point and the process variable are the same, then the controller is a very happy little box. It doesn't have to do anything. It will set its output to 0. However, if there's a disparity between the set point and the process variable, we have an error, and corrective action is needed. In our house, this will either be cooling or heating, depending on whether the process variable is higher or lower than the set point, respectively. Let's imagine the temperature process value in our house is higher than the set point. It's too hot. The air conditioning is switched on, and the temperature drops. The sensor picks up the lower temperature, feeds that back to the controller. The controller sees that the temperature error is not as great because the process variable, or temperature, has dropped, and the air conditioning is turned down a little. This process is repeated until the house has cooled down to 22 degrees C, and there is no error. Then a disturbance hits the system, and the controller has to kick in again. In our house, the disturbance may be the sun beating down on the roof, raising the temperature of the air inside. So that's a really basic overview of a simple feedback control system. Sounds simple, doesn't it? Unfortunately, in the real world, we need a controller that is a bit more complicated than the one described above, if we want top performance from our loops. To understand why, we will be doing some thought experiments where we are the controller. When we have gone through these thought experiments, we'll appreciate why a PID algorithm is needed and why and how it works to control the process. We will be using the analogy of changing lanes on a freeway on a windy day. We are the driver and therefore the controller of the process of changing the car's position. Here's the block diagram we used before, with the labels changed to represent the car on a windy freeway control loop. Notice how important closing the feedback loop is. If we remove the feedback loop, we would be in open loop control and would have to control the car's position with our eyes closed. Thankfully, we are under closed loop control, using our eyes for position feedback. As we saw in the house temperature example, the controller takes both the process variable and the set point signals, which it then puts through a black box to calculate the controller output. That controller output is sent to an actuator, which moves to actually control the process. We are interested here in what the black box actually does, which is that it applies 1, 2, or 3 calculations to the set point and measured PV signals. These calculations, called the modes of control, include proportional, or P, integral, I, and derivative, D. Here's a simplified block diagram of what the PID controller does. It is really very simple in operation. The process variable is subtracted from the set point to create the error. The error is simply multiplied by 1, 2, or all of the calculated P, I, and D actions, depending which ones are turned on. Then the resulting error times control actions are added together and sent to the controller output. These 3 modes are used in different combinations. P is sometimes used, PI is most often used, PID is sometimes used. PD is rarely used, but can be useful for controlling servo motors. So let's now get an intuitive feel for how each control action works. In other words, let's understand what goes on in the P, I, and D boxes in the block diagram above. To do this, we will be using our analogy of driving a car on a highway and using the principles of PID control to move the car into another lane. Here's a diagram of the controller when we have enabled only P control. In the proportional only mode, the controller simply multiplies the error by the proportional gain, AP, to get the controller output. The proportional gain gain is a setting that we tune to get our desired performance from a P-only controller. We've already pointed out that driving a car with your eyes open is analogous to feedback control where you are the controller. To take this analogy further, think about when you change lanes on the highway. Everything is instinctive, of course, but if you analyze your actions, the course of events goes something like this. You have to first choose an initial steering angle. In reality, you slowly increase the steering angle, but for the sake of this thought experiment, assume that you quickly turn the steering wheel to an immediate initial angle. The car immediately starts to move towards the center of the next lane. Now, you don't want to wait until you're at the center of the next lane to start correcting your steering, so what you intuitively do is reduce the steering angle as you get closer to the target position in the next lane. In other words, as your position error reduces, so does the control action. As the error reduces, so must the controller output. So the safest approach to changing the lanes successfully is to start with a small angle and slowly reduce it as you get closer to the next lane. The problem with this is that if you're in a hurry to get into that lane and you choose a really conservative or rather small angle initially, you will take a long time to get there. It's the same with proportional control. A small proportional gain, Kp in the diagram, is the safest way to get to set point, but your controller performance will be slow. Okay, so you need to get into the outside lane before the approaching Porsche slams into your rear. You wrench the wheel to a really steep angle and start correcting as you get closer, but your momentum has taken you over the center of the next lane and you're rapidly approaching the opposite side of the road. Because you are consistent, just as a PID controller is, you wrench the wheel in the opposite direction just as hard as before. And guess what? Now you've overshot back to the other side of the lane. Before you know it, you've gone unstable. You are in a vicious cycle of lurching from one side of the lane to the other and back again. That's why too much P gain in a control loop sends it unstable. The actuator doesn't back off quick enough, you overshoot, and then make the exact same mistake going the other way, and on and on. So the trick is to find a P gain that is high enough to give you the speed of response that you need, but not so high that you go unstable. So why don't all control loops use a P-only controller that is beautifully tuned not to overshoot the set point and leave it at that? The answer is disturbances. Disturbances in a control loop require more than just P. Previously, you were driving your car down the freeway, and being a good driver, you had found the perfect angle for changing lanes nice and quickly, but without going unstable. Now you're driving along feeling pretty content with yourself. Every time you change a lane, you move the wheels to just the correct initial angle thanks to a well-tuned proportional term. And as you drift over to the next lane, you start reducing your angle the closer you get to your final position. As your position error goes to 0, your steering angle goes to 0 too, and you end up in exactly the right position every time. AC/DC is on the car stereo and life is good. But then you notice a sign warning of extreme crosswinds for the next 10 kilometers just as you decide to change lanes again. You turn your wheel to the right to your pre-calculated initial angle and find that the car only moves a little to the right before continuing straight on. The crosswind is so strong that as you were moving closer to the target lane and reduced your steering angle, the smaller steering angle was being fully counteracted by the strong crosswind. You are still moving in a straight line, although you are steering slightly to the right. The result is that you are offset from your target position by a fixed amount, the position error. And because the rules are that the steering angle must be proportional to the position error, we are behaving as a P controller, remember? You are a bit stuck. You can't change the steering angle because the error isn't changing, and the steering angle only changes when the error changes. We need some new rules for steering this thing. What would happen in practice is that we would use trial and error under these new crosswind conditions to get the initial angle just right, so that once again we end up in the perfect position. Let's assume that we bias our steering angle in this way to take account of the crosswinds. But then there is a downhill and we start speeding up and find that our pre-chosen angle overshoots, because the faster we're going, the faster we'll move across the highway. So we try trial and error again, and just as we get the steering angle bias correct for our new speed, the gradient changes and we start slowing down. What a bummer. It's time to change our bias angle again. Let's think about what is happening here. We have a P-only control loop that is working beautifully until some disturbances started hitting us. We had to manually bias our initial steering angle each time the disturbance changed. This is analogous to a P-only control loop, where we are continually changing the P gain to cope with the changing disturbances, not an optimal situation. We call this changing of the gain manual reset, because we have to manually reset the gain whenever a disturbance changes. Wouldn't it be nice if we could automatically reset the gain? Guess what? Integral action is also called automatic reset. And guess what it does? That's right. It automatically resets the bias of the gain until the error is 0. Back to our car with a human controller. So you're driving along with your wheels at a fixed steering angle, but because of the strong crosswind, you're moving straight ahead. But you want to be moving sideways to your target position in the next lane. What do? You do exactly what the integral term in a PID controller does. You start to increase your steering angle, and you keep increasing it until you start moving sideways. This is where the integral action is used to overcome the deficiencies of proportional action. Proportional action is simply the P gain multiplied by the error. If the error is holding constant, but you aren't at your target set point yet, you will be stuck. This is called an offset, and is the problem with P-only control. The addition of integral action overcomes this deficiency. If there is an error between this set point and the process variable, integral action will start to ramp up the controller output until things start moving again. Mathematically, it increases the controller output by the integral of the error. What does this mean? Remember our definition of integration as the integral of a signal is the sum of all the instantaneous values that the signal has been from whenever you started counting until you stop counting. Translating this to a control system, it means that the integral action will simply start adding up all the error values, resulting in a ramping signal if the error is non-zero. Of course, to make sure that you ramp the error just enough, you need to be very careful in tuning the I constant. Pretty straightforward, isn't it? So now we have pretty good control of our car steering. We have a P term, which immediately looks at the instantaneous error between where we are and where we want to be, and provides us with a good initial angle to turn our wheels to. As we get closer to our target position, the P action reduces steering angle as the error decreases. In parallel with this P action, the I action starts to bias the steering angle by continually adding to the steering angle as long as there is a position error. When there are no disturbances, the integral action has the effect of simply making the steering angle a bit steeper, improving our controller performance by reducing the amount of time it takes to get to our destination. However, where our I action makes a big difference is where we have a disturbance, such as a crosswind. In that situation, our I action continues to ramp up our steering angle until we have enough angle to break through the crosswind and continue to our destination. A match made in heaven, the PI controller. If we put proportional and integral action together, we get the humble PI controller. The diagram below shows how the algorithm of a PI controller is calculated. The tricky thing about integral action is that it will really screw up your process unless you know exactly how much integral action to apply. A good PID tuning technique will calculate exactly how much integral to apply for your specific process. But how is the integral action adjusted in the first place? The way to adjust how much integral action you have is by adjusting a term called minutes per repeat. Not a very intuitive name, is it? So where does this strange name come from? It is a measure of how long it will take for the integral action to match the proportional action. In other words, if the output of the proportional box on the diagram above is 20%, the repeat time is the time it will take for the output of the integral box to get to 20% too. And the important point to note is that the bigger the integral action, the quicker it will get to this 20% value. That is, it will take fewer minutes to get there. So the minutes per repeat value will be smaller. In other words, the smaller the minutes per repeat, the bigger the integral action. To make things a bit more intuitive, a lot of controllers use an alternative unit of repeats per minute, which is obviously the inverse of minutes per repeat. The nice thing about repeats per minute is that the bigger it is, the bigger the resulting integral action is. Okay, so the combination of P and I action seems to cover all the bases and do a pretty good job of controlling our system. That is the reason that PI controllers are the most prevalent. They do the job well enough and keep things simple. Great, but engineers, being engineers, are always looking to tweak performance. They do this in a PID loop by adding the final ingredient, derivative action. Imagine you're back in your car and you're in a rush to get back home before the football game starts, so you put the pedal to the metal. After a while, you need to change lanes again to pass a slow-moving vehicle. You move your wheels to the preset angle that worked so well earlier. However, because you're going faster, you start to move across a lane quicker. You end up overshooting the target lane and have to turn the wheels in the other direction to get back on track. You may get into the target lane eventually, but the maneuver wasn't as slick as you'd come to expect. Imagine if, immediately after you had turned the wheels, the car had itself worked out that you were moving across the lanes a bit too fast, and that at this rate you would overshoot the target unless the angle was reduced. Imagine if the car had then taken it upon itself to correct your steering angle, reducing it so that you had minimal, if any, overshoot. Well, that's the idea behind derivative action. As you might have guessed, derivative action uses the rate of change of the error to calculate its contribution to the controller output. So let's think through how that actually works in the above example. When the wheel is turned, the position error of the car R starts to reduce rather quickly as you get closer to the target lane. In other words, the rate of change of the error is large and negative. This manifests itself as a negative derivative action, which works to reduce the steering angle, which in turn will reduce the overshoot. The trick, of course, is to have just enough D to remove the overshoot, and that's where proper tuning comes in. Trial and error just doesn't cut it. So adding derivative action can allow you to have bigger P and I gains and still keep the loop stable, giving you a faster response and better loop performance. If you think about it, derivative action improves the controller action because it predicts what is yet to happen by projecting the current rate of change into the future. This means that it is not using the current measured value, but a future measured value. The units used for derivative action describe how far into the future you want to look. In other words, if derivative action is 20 seconds, the derivative term will look at the current rate of change 20 seconds into the future. The big problem with derivative control is that if you have noise on your signal, which looks like a bunch of spikes with steep sides, this confuses the heck out of the algorithm. It looks at the slope of the noise spike and thinks, holy cow, this process is changing quickly. Let's pile on the D action, and your control output jumps all over the place, messing up your control. Of course, you can try to filter the noise out. My advice is that unless PI control is really slow, don't worry about switching D on.